Well, hello everybody. My name is Steve Sapsford. I'm chair of the Powertrain Systems and Fuels Group. We represent members who are interested in powertrain systems generally, all the way from internal combustion engines through all forms of hybridization to electric drives and fuel cells, and also the complete drivetrain and all the associated technologies such as renewable fuels. So welcome to our annual lecture. We do this every year, normally as part of our AGM, but we've not been able to do all of that due to the current circumstances. But we really wanted to keep going with the lecture, so it gives me great pleasure now to hand over to Alan Tolley from JCB, who's going to introduce the presenter for this year's lecture on the world's fastest tractor.
Good afternoon. Welcome to this lecture. A very exciting topic, the world's fastest tractor. We had originally planned to have sort of done an extra event by now, and we were going to tell you about that. But unfortunately, due to the epidemic, we haven't done that. But keep your eyes and ears peeled for the future. That might happen. But we've still got a very exciting topic to talk about here. And the presenter today is Alex Skittery. So Alex was a project manager for the world's fastest tractor. So Alex, with a young team of apprentices, new graduates, exciting project for them. So Alex managed this project and took it to conclusion very successfully. So Alex is going to present a summary of the world's fastest tractor, including the powertrain for that tractor. So I'll hand over to Alex now for the presentation.
Tractor.
Tractor's job, landwork cultivation, leading, tail rowing, de-stoning. As long as you call it digestate, poo spreading, mug spreading. Yeah, it's shit spreading, isn't it, really? That's we all know, don't we?
Guy Martin.
I just want to go as fast as humanly possible on whatever I'm on. Whether it's a push bike, whether it's a car. I love going fast. I love it. Took a smack on me head, I know that. But I'm alright, no one's died. No one's died.
JCB.
They're amazing things, aren't they? Piece of kit, eh? Oh, it's JCB. They don't mess about with it. They don't mess about. A trick, innit? They're doing it. They're doing it. $150 miles an hour or something like that. That's a proper record. That is a proper record. Not easy done though.
Hello everyone, and welcome to my lunchtime lecture on the world's fastest tractor. So my name is Alex Skittery, and I was lucky enough to be the project manager for this amazing project. So before I get into all the details of the tractor, I'll just do a quick introduction to myself, and then we'll go through what I'm going to cover in this presentation. So I've been with JCB for 6 years. Prior to that, I studied agricultural engineering at Harper Adams University. When I got to JCB, I first worked in design for telehandlers, and then I worked in the research department, and I'm finally now working on tractors. So, as I mentioned, last year we had this amazing project designing and building the world's fastest tractor. So in this presentation, I'm going to briefly cover why we did the project, the challenge we had, what we did to achieve it, and then obviously the results. So it's a question we get asked quite a lot, why do it? Why bother with this project? Well, it all started really with the chairman of JCB, Lord Bamford. And he's always had this desire to have the fastest tractor, and we build Fastrac tractors, so that's the name of them. They are the world's fastest production tractor, and we started to notice a few of other tractor manufacturers were trying these speed records. A few other people like Top Gear, for example, and we thought, well, we can probably do a bit better than that. So that was really the catalyst for all of this. JCB are no strangers really to world record attempts for speed. So we hold the world's fastest backhoe record at 96 miles per hour. And then, of course, we hold the world's fastest diesel car record at 350 miles per hour. And this car actually had two diesel engines in it, one that powered the front wheels and one that powered the back. So as well as the desire to do the project, really we wanted to showcase innovation, and really JCB holds innovation at the heart of everything that we do. So I'll talk a bit about all the future technology and that new tech and interesting stuff during this presentation. It was also all about teamwork, and it was actually a very young, keen team that partook in this project. I think we had a median age of about 23, and then obviously we had quite a lot of help and advice from some of the more experienced engineers at JCB. And then, of course, fun. I mean, if you can't be having fun at work, you may as well go and find something else to do, because you spend a lot of time there. So it was a really good, fun project to work on, but it really was conducted with safety at the forefront of absolutely everything we did. We made sure that it was always our primary concern right from the get-go. So moving on to the next section now of the presentation, the challenge. So the tractor you can see in front of you is what we started with. So this is a 4000 series Fastrac, so that's the model number. It weighs 8.5 tons. Its maximum engine horsepower is about 240, and its maximum speed is 43 miles per hour. So the challenge we got set is make that go over 100 miles an hour, and the aim was it's got to go 150 miles per hour. So how do we sort of approach that? Well, the first thing was obviously the speed, which I just mentioned. The target was 150 miles per hour. Next, we looked at where could we do the record. We looked at lots of places all around the world, but we sort of settled on the UK. We wanted to keep it on home turf. It just felt right to do it in the UK. So we actually ended up conducting the record attempt at Elvington runway. One of the conditions of the Guinness World Record that we achieved was that it had to be a very flat track, and you had to conduct the record in both directions. So you zoom from left to right down the runway. You then had 1 hour to turn around at the end, and then you'd have to zoom back down the other way. And the world record speed was the average of the middle kilometre going in both directions. So really a flat, long track was what we were after. And this was the longest one that we could find at about 3.2 kilometres. So we knew the speed, we knew the track. We then produced a simulation model that iterated different weights, powers, coefficient of drag, gear ratios, a whole raft of different inputs, just to try and generate a set of targets that we could all define right at the beginning of the project and all design this vehicle to. So I'll flick on to the next slide. So the model spat out, many different outputs, but really the three main attributes of the machine were we had to get the weight down to 5 tons to help us accelerate up to speed. We had to improve the aerodynamics quite dramatically. So that's the CDA number, so that's the coefficient of drag times by the frontal area. And we also had to increase the engine power to over 1,000 horsepower. So those are the targets. And now I'll spend some of the presentation now taking you through each of those and how we achieved those. So in front of you, you can see the finished machine. This is the world record tractor. And really what I'm going to do is explain some of the internals. So some of the bits underneath the skin that you can see. So the first one is mass. As I mentioned before, the machine weighs 8.5 tons. And we had to try and get that down to 5. So, 3.5 tons. Someone told me that's the same as a Range Rover and a Mini we had to remove from the tractor in terms of weight. So a lot to consider. So we started with the low-hanging fruit. We took off some of the bits off the tractor that we didn't need. For example, the tow hitch at the back that we used to lift up ploughs. It could be fitted onto the tractor, but for going in a straight line on a speed record, we didn't need that fitted. We then looked at the remaining parts and decided what we could produce or manufacture from aluminium instead of steel, which is normally our material of choice on our machine. And a key area of the machine that we reduced the mass quite a lot of was the chassis. Now, it was based on the production chassis, so the one that we fit to the tractor today, but we actually optimized it so that it was tuned for the duty cycle of going in a straight line fast. So we used some FEA and topology optimization software for that. The blue image you can see on your screen was the output from that optimization software. And as you can see, it sort of comes up with a few weird and wonderful shapes. We then produced a model which we could manufacture. So instead of casting it, for example, we made it from sheet metal. And then we performed the FEA, so the finite element analysis on that, just to get a really nice optimized chassis. So after mass, the next thing on the list was aerodynamics. And normally we don't worry too much about aerodynamics for our machines. They're only going at a relatively low speed. So really the main resistive forces on those machines at those speeds are the rolling resistance, for example. So we didn't really have a huge amount of experience of this. We went to our friends at Williams Advanced Engineering, and they helped us extensively with their aerodynamic knowledge. And I mean, we used CFD, so computational fluid dynamics, which basically produces it's a virtual wind tunnel. We blasted 150 mile per hour air and crosswinds at the machine, and we really tried to optimize the aerodynamics so it slid through the air with minimal resistance. So some of the key aerodynamic features that we added to the machine were, we firstly reduced its frontal area. So the whole thing is about 400 mil lower than normal and 300 mil narrower. We then added the front bumper you can see there, or the front splitter. We added, we changed the roof design and added fins onto the rear of the cab. We added an under tray as well. Loads of different tweaks just to try and get it to slide through that air as easy as we could. And I mean, we sort of had regular reviews with Williams, and we were kind of struggling to visualize this this CFD output. You know, PDFs are great, but we just wanted something better, something that could really help guide our design. So we actually helped, well, they developed this technique for us, and we helped sort of get it all up and running in terms of using virtual reality to try and visualize exactly where this air was going and how the machine was disrupting that airflow. So it was really good, a really immersive experience that helped guide the design quite heavily. And here you can see that the aim of the game is to try and keep the air yellow. So yellow is undisturbed air. Anything red is air that's speeding up. Anything blue is air that's slowing down, which increases your coefficient of drag. So yeah, a really, really useful tool that helped us tweak the bodywork really effectively. So the next thing is looking at the driveline. So I'll talk about the engine in the next section, but really that engine's producing that target of over 1,000 horsepower, and we need to try and transfer that down to the ground. So the first link in the chain after the engine is the clutch. We were asking quite a lot from the clutch. It needed to be able to handle a really high torque capacity. We needed to be able to slip it for an extended period of time, over 15 seconds, just to get the machine rolling, because it was geared so highly. So we looked at loads of off-the-shelf multi-plate dry clutches, but we just couldn't find anything that ticked the boxes. So we actually ended up using a clutch that we fit to our tractors, or some of our previous tractors, which was a oil immersed 8-plate wet clutch. And this, I mean, it ticked all the boxes really. It was simply supported so that it didn't excessively load the crankshaft of the engine. It had a really high torque capacity. I mean, this thing's designed to have a tractor that's fully loaded with about 15 tons in the trailer, slammed into reverse, going down a hill while you're going along, and it can slip and not overheat. So it's got a really, really good heat dissipation capacity. It's also electronically, there's an electronic solenoid control on there, which varies the oil clutch pressure. So this meant that we could tune it to whatever we wanted, just to get that machine running really, really well off the line. A launch control mode almost. We then coupled that to a 6-speed manual transmission, really because it was nice and light and simple. I think the whole thing weighed about 250 kilograms, cable operated, not a huge amount to go wrong. So just a nice, simple racing gearbox. That then fed a axle, and this is actually an axle off one of our tractors, modified slightly, in that we locked up the center differential so that we didn't get excessive wheel spin off the line, and we also locked up the epicyclic gears in the hubs just to get that gearing nice and high. But other than that, a standard tractor axle. As I mentioned previously, we could have towed a plough behind it if we really wanted to. So the next step in the driveline chain is the tyres. You know, we've got to put all that power down to the ground. And I think this was probably the cause of most sleepless nights for me during the project. I mean, we were asking quite a lot of the tyre. It was important to us that it still looked like a tractor tyre, just to sort of retain that DNA of being a proper tractor. So it had to be safe and stable at 150 miles per hour. And as I mentioned, it's still got to look like a tractor. So we worked with one of our suppliers called BKT. they got a standard tyre, so we used a standard tractor tyre mould. We changed the compound slightly, so we added a bit more natural rubber so that we enhanced the grip characteristics of the tyre. We added 2 steel belts to the tyre as well, and they were really to help stop the tyre grow at such high speeds. I think we measured on the rig video that you saw at the beginning of the slide there. I think it grew about 20 millimeters when it was spinning at 150 miles per hour, and that's 20 millimeters in diameter. We also shaved the tread down a bit, just to try and reduce that force at the outer edge of the tyre, and also get them a bit more stable, so they weren't moving around on the tread blocks and increasing the rolling resistance just from that tyre hysteresis. So we did quite a lot of FEA analysis, made sure in the virtual world the tyres were up for the job. Of course, nothing beats a good rig test. So we tested them on a rig in Germany, designed for aircraft tyres, because it's the only rig we could find that would actually spin the tyres up to the required speed. And that was really useful. It gave us good sort of limits on temperature. We knew, how warm the tyre was getting at different speeds. But we also used the rig not only to simulate the record run, but also to see, well, what is the limit of the tyre? And we definitely did find that limit. The picture that's just appeared on your screens shows the tyre blown up, and it did create quite a large bang. So it's quite an important exercise because it told us how warm the tyre could get before it went bang, but also the failure mode. And we found that actually the tyre started to vibrate excessively before that bang occurred. So we were able to instrument that on the machine, and we actually had live vibration, temperature and air pressure monitoring. So if anything got to those ceiling limits that we measured on the rig, we could tell the driver and he could just stop the machine. So the next bit is engine. So, the challenge was we were allowed to do the projects, but it had to use a JCB diesel engine. So we used our JCB 672. So this is a 6-cylinder, 7.2 litre engine that we fit to some of our excavator machines. And again, like the tractor, we wanted to try and keep as much of it as common as possible. I think on the tractor, over 50% of the bits were from a standard tractor, and that percentage, it was even larger for the engine. I mean, we kept the block the same, the head, the pistons, the crank, the rockers and the rocker shaft, water pump, oil pump, fuel lines. So as much of it as possible was kept standard. But of course, we wanted to try and get more than 240 horsepower from it. So how do you do that? Well, simply more air and more fuel. That gives you a bigger bang, more explosion. So that gives you more power, but obviously quite a lot more heat. So first one we'll look at is more fuel. So we achieved this by fitting a larger fuel pump and larger injectors from a larger capacity diesel engine. These injectors actually ran at 2.7 litres per minute flow rate and at about 2,500 bar. So they were pumping a lot of fuel into our cylinders. I think on the 150 mile an hour run, we averaged about 5 miles per gallon and about 200 litres per hour if you extrapolate it out. And to put that into comparison, a normal tractor running at full power, ploughing a field, would be using about 35 litres per hour. we used standard diesel as well, so red diesel that we'd normally use in our construction and agricultural machines. So as well as more fuel, we needed more air. So we sort of employed 3 strategies for this. The first step was a larger turbo. So the green image you can see in front of you was the standard turbo, and the red one is the turbo we ended up with. So this was pumping quite a lot of air into the engine. You know, it was running at about 5 bar of boost pressure and about 1,000 litres of air per second, which is great when the engine's running fast. But running slowly, when that exhaust energy to accelerate that large turbine is just low, you get a lot of turbo lag. So we sort of employed the next couple of strategies to try and reduce that lag. So the first one we looked at was an electric supercharger from Federal Mogul. This is starting now to be fitted to some commercial diesel truck engines. We ran it at 24 volts and powered that with a set of lithium-ion batteries just to try and keep the weight down. And it was a really impressive bit of kit. It could spin from 0 to 50,000 RPM in less than a second. And what this did was below anything, I think it was about 2,000 engine RPM, this would kick in and actually feed air directly into the turbine of the engine, of the turbo, sorry. And then we just use pressure sensors to work out, well, when the turbo is breathing more air than the electric supercharger, it would automatically turn off. So that was really good, helped a lot with our turbo lag issues, but we did still have a bit of a turbo lag. So we looked at a few different options. We looked at, could we use nitrous oxide, but we thought, well, that's probably a little bit boy racer for us. And we sort of arrived at quite a simple solution, really, and it was an air pulse system. So what this did was it would inject 20 bar of air into the exhaust manifold, which would spin up the turbo. And we used this primarily when we were setting off the line, but also during each gear change. So it's probably about a 5-second pulse every gear change on the machine. So this would use a full scuba tank of air per run, and that was how we were holding and delivering that air. So you can see that was one of the tanks fitted to the back of the machine. So we've got more air and more fuel, which is giving us more power. That increases the heat output, or the heat generated from the engine. So we employed a number of measures to try and keep the engine down and just stop it from melting. It was, I think, aside from tyres, it was one of the hardest things to get right. This was. We wanted the engine to be nice and warm to be able to start it, and that's because we were running quite a low compression ratio of about 11 to 1 compared to our standard 20 to 1. Just so we could keep our cylinder pressures down when we were pumping all that air into them. But at the same time, we wanted the air inlet into the engine nice and cold when we were running. So there was quite a fine balance between hot and cold. So to preheat the engine to get it running, we plugged in an external water heater into the engine coolant circuit. That would preheat the block, so both the water and the oil, to about 80 degrees. We then also heat the air going into the engine with some grid heaters. So that was getting it nice and warm, and then as soon as it started, we wanted to flick over to that nice cold air. So we used a water charge air cooler to cool down that inlet air. So it was quite an impressive unit. I think we could get down to from about 240 degrees down to about 10 degrees in less than a second. So that's turbo out through the WCAC before it went through into the inlet manifold of the engine. So that's a lot of heat to take out of air, and we found that actually using a water radiator as a heat exchanger was just, it didn't have enough capacity. So we ended up having a 60-litre water tank at the front of the machine, which we actually filled with 25 kilograms of ice. And this really helped to cool down the water and take all that heat out of that air. And we'd used 25 kilograms of ice in one run down the runway, so that's probably in just over a minute we'd burn or we'd melt all of that ice. There was quite a few trips to Tesco's to clear out the freezers just to try and keep the tractor stocks up when we were testing. As well as the WCAC, we also injected water into the air intake, just to try and control those cylinder temperatures and keep exhaust temperatures down. Normally, the radiators of the machine, so both for the oil and the water, are positioned at the front of the tractor, but due to the size of them, we just didn't have the room. So we ended up putting them in the sides of the tractors, which you can kind of see in between the wheels here on the schematic. So we had the engine coolant radiator at the bottom and the oil radiator you can see at the top there. And these relied purely on ram air. We didn't have any cooling fans. So it was really important when we were designing this bodywork to try and funnel and channel air into these radiators. So there's a lot of CFD analysis to try and optimize that. We also employed piston cooling jets. So these splashed cold oil underneath the cylinders, just to try and keep the temperatures down and stop them from melting. So that was the system. We did quite a lot of simulation work just to try and simulate how that would all work during a run, just make sure that things weren't going to get too warm during the run. So here's just sort of an image of the machine, and you can see some of the key features here, like the charge air cooler sat at the top there. So that was sort of sculpted around the bonnet just to try and package it underneath that tractor bonnet. You've got the ice tank, which sat in front of in the front bumper of the machine, and you can see the radiators on the side there with their air intakes. So quite a few strategies there just to try and keep this engine nice and cool. Okay, so now I'm just going to show you a video. This is the engine running on a test bed down at Ricardo. So Ricardo helped us extensively with this engine development. And as you can see, the torque really starts to jump there when the engine gets to about 2000 RPM, and it absolutely shoots up. And you can see the exhaust there glowing red, and it got very, very warm. We were approaching 1000-degree temperatures there, and that sudden increase in torque was primarily when this air pulse system was kicking in, really spinning that turbo up to speed. So we tested the engine on the test bed. We could see things were getting quite warm. So as a precautionary measure, we ended up 3D printing large sections of that exhaust manifold out of Inconel, just to make sure that it copes and didn't deform excessively during testing. So the result of all that work, all that engine development, was an engine that produced 1006 horsepower at 3100 RPM, and a massive 2,370 Newton meters of torque. And this was actually the torque curve we used for the record-breaking run, and we measured these values with a strain-gauged prop shaft on the machine. So this is actually what was being fed into that axle to give us that world's fastest tractor run. So on the screens now, you can see this is the actual speed trace from GPS of our fastest tractor run. So the average speed over the flying kilometre was 135.191 miles per hour. And that actually was a peak speed of 153.771. And I mean, what this showed us is, and it was reflected in all our simulation models, was actually if we had a longer runway, we could have definitely increased that world record speed to over 150 miles an hour. And you can see that on the graph here. The tractor's actually still accelerating quite rapidly while it's passing through that measured kilometre. So, you know, in the future, if we decide to dust it off and have another go, we'll try on a longer runway and we'll see what we can get. So now this is just a video of one of the runs before our world record event. So you can see this is Guy Martin driving here, and you can see the acceleration. I think it was 0 to 60 in less than 6 seconds, which for a 5-ton machine was pretty good going. You can see him changing gear, so now he's in 5th gear and it's just foot to the floor. The gearbox actually had 6 gears, but we didn't ever use 6th gear just because it was geared way too high. So you can see it's quite stable. It used standard suspension, steering, brakes as the standard tractor, so we really didn't have to modify any of that geometry, and it was a really stable run. Guy said, you know, he was so surprised at how smooth it was to drive. So you can see now he just flicks it into neutral, turns the steering and turns around at the end, and this is where the pit crew would jump in. We'd refuel the machine, we'd check it all over, check all the tyre temperatures, all the machine parameters. We'd check all the engine data logs. We'd fill him back up with ice, ready for the next run. And there we are. There's the team that was, you know, integral to the project, and also some of the wider team. So that's the end of my presentation. I hope it was interesting, and I think I'm going to stop it there, and we'll open the floor to any questions. Thank you.
Thanks, Alex. It's Alan Tolley here again. So we've got some questions now. There's some questions here being posted, so we'll go through those. The first question is about the braking. What modifications did we make to the braking system for these high speeds? Perhaps you could answer that, Alex.
Yep. Okay. Can you hear me, Alan, on this?
Yes, I can.
Oh, brilliant. Okay. Yeah. So we actually end up using the standard braking system that we fit to the tractor, and I think our braking system is a bit different to other tractor manufacturers purely because of the speeds that our standard Fastrac runs at. So we actually have a full ABS external brake disc and caliper brake system fitted to the machines, and this is a twin caliper per brake disc, whereas a lot of other tractor manufacturers will use inboard brakes which are located inside the axle, running in the axle oil. So yeah, it was pretty standard. We did lots of FMEAs and lots of testing to make sure that they weren't going to get too hot, for example, when we were trying to brake from such a high speed. Lots of testing, but we ended up keeping it all standard, same pad material and everything.
Yeah, I think it's worth mentioning with the brakes, of course, for the standard tractor, which in itself is quite a fast tractor. The braking system has to handle both a heavier tractor and very, very heavy trailers. So, there might well be a total vehicle mass of approaching 30 tons or so there. And hence the braking system is a very high power, effective system.
Yes.
I've got another question from Jim, who's interested in the speed at which the tyre exploded. So maybe, Alex, it's worth talking about what actually happened on that rig test a bit.
Yeah, well, we tested the tyres to, I think it was about a peak speed of 164 miles per hour, I think was the top speed we went to. But actually the tyre exploded because we ran it at that high speed for an extended period of time. I think it was after about 7 minutes that it went bang. And we knew that we weren't going to be going at that peak speed for anywhere near that amount of time. I mean, if you look at the graph, which I think I can see on my screen, so I hope other people can see it, but we were only at the top speed for a few seconds, really. But as I said in the presentation, we just wanted to try and see what it was capable of, really, before it went bang, and just get those values which we could then use when we were actually running the machine, and just give us some confidence that they weren't going to go bang when the driver was driving the machine.
Okay, thanks, Alex. I've got another question here from David, who's interested in how we reduce the compression ratio of the standard pistons. So perhaps I'll answer that one.
Yeah, that sounds like a good one for you, Alan.
When we say standard pistons, we actually used production castings, but the pistons were machined by the supplier explicitly for this engine. So it had a bowl design, which fitted within the limitations of the casting to give sufficient strength, which took our compression ratio down. I think we ended up at about 12-1 actually. Quite an open bowl, because the bowl had to stay within the profile of the piston for sufficient strength. So not a bowl that you would have necessarily developed for best SFC or good NOx emissions. So that's what we did with the standard pistons, standard piston castings, this engine. Let's see, I've got a few more here coming in quite rapidly. Let me have a look at these. Yeah, quite a good general question here from Umar. How has this project helped you with the tractors and excavators in general at JCB? So perhaps, Alex, now having moved on to tractor engineering, you can share some experience with that.
Yeah, of course. Well, a lot of it was trying to optimize the machine. So we tried to make it lighter. We tried to make the tires more efficient and reduce the rolling resistance. So a lot of that we're carrying forward into the next generation of tractor design, really, because fuel's not getting cheaper. Farmers aren't making any more money. Wheat price has been stagnant for the last 15 years now. So they're looking at ways to try and try and maximise the inputs really that they put into their farming system. So yeah, that comes down to the machine design. Things like, you know, tyre rolling resistance we're looking at a lot at the moment, because our tractors probably spend half their time on the road and then half their time in the field. So trying to find tyres and systems that help reduce that rolling resistance is really key. And a lot of the learning we had on Stag with the World's Fastest Tractor project in terms of different compounds and is proving really useful with our future machines. You got any other points
thanks.
to add on that,
Alan? I think, you know, from an engine point of view, it's you know, they always should say racing improves the breed, but I mean it does give a reference in terms of, you know, a reference point in terms of the strength, capability of the base engine. You know, we do lots of testing on engines at near or slightly above the production maximum rating, but it is good to see what happens to some of those components when you really stress them, and therefore that information does feed back into the general knowledge about the capability of the engine. Good. I've got a question here from Will about what were the gear ratios used, and I mean, I'll have a go at that one if you like, Alex, because I think it's the gearbox we used. It was an off-the-shelf gearbox. You know, actually, I think its production use is in buses and medium trucks. So we chose a manual gearbox really because of the efficiency. We didn't want to be losing anything going through the gearbox. And this gearbox in its fifth gear, I think it was the fifth gear, was highly efficient, 99% plus efficiency. But it's an off-the-shelf gearbox, so the ratios that we had were really the ones which came with the gearbox. We had control over the axle ratios because that was something we produced ourselves. So the fact that it's a 6-speed gearbox meant that we would use 4 or 5 of them, and that proved to be to work well. Though of course it gave us some challenges, as Alex was talking about, in terms of getting the turbo spinning and getting the torque out of the engine at the lower speeds. Sometimes when we change gear, so there's a whole learning there of the driver about when to change gear and also the system of air boost, etc.
Yeah, I think it was in top gear. I mean, we only used 5 of the gears out of the 6, but that was a 1-to-1 ratio coming out of the gearbox.
Yeah. So here's one, Alex, from Malcolm. Can it still be used as a tractor?
Yeah, we do get asked this occasionally. Yes, is the answer. We designed it right from the beginning so that if we wanted to, we could take it out into a field and do an agricultural task. So, for example, you know, pulling a set of discs to cultivate the ground. And we can achieve this because we've used a standard tractor axle. All the suspension mounting points are exactly the same as a standard tractor. So that means that you know, we could probably wouldn't be able to go farming for too long before we'd run out of fuel. It only had a 20-litre fuel tank, I think, from memory, whereas the normal tractor has a 400-litre fuel tank. But it could definitely do something, and I'd love to get it dusted off and get it out the shed one day and do that with it.
Perhaps another good one here for you, Alex, from John. What was the impact on the team which formed around this project, and how do you harness that for the business?
Yeah, good question. Well, it was actually about this time last year where we had completed the record, and then we were all sort of wondering what we'd be assigned to next. And we actually all got, the whole World's Fastest Tractor team got put on by Lord Bamford to work on a new tractor project. So we were sort of all kept together, and we were all put on developing the next generation of tractors, which will be in production in years to come. So yeah, it's been really good, and I think just that shared sort of sense of urgency and that shared purpose has sort of made us really gel quite well as a team, and yeah, we've sort of got the confidence we can get the job done now.
There's a question here from Robin. He says, well, how much is it to buy? So I think the actual tractor's not for sale. But I think, Alex, there was a series of fastest tractor models produced, wasn't there?
Yeah, they did some special edition Fastracs, 4000 series. So, they had a few modifications to them just to sort of commemorate the record. I think you could probably get one for about £140,000. But yeah, the fastest tractor is yeah.
Right, let me see. There's a few other questions here. Let's have a look. Also, perhaps an interesting one from Matthew, because it was something that we thought about a lot, especially early in the project. He's asking, was there restrictions on how much unlike a tractor you could make it?
Yeah, I mean, the governing set of rules that we were adhering to were the Guinness World Record rules for the fastest tractor, and then in brackets modified. And actually, when we went to Guinness to get clarification on those, it was very, very vague. I don't think they really had a huge amount of information or even rules to go with what modified meant. For example, the Top Gear Traxor, so the orange-looking machine that was on one of the episodes on Top Gear, that was classed under the same record. But actually, all that was a pickup truck with some big wheels put on it, and a tractor bonnet to make it look like a tractor. So I think you could stray quite far from it being an actual machine. But the way we wanted to do it was keep it as much like a standard tractor as we could. So we pretty much got the standard machine in CAD and started modifying bits where we needed to. And I think, as I said in the presentation, there's probably over 50% of the bits were from a standard Fastrac.
Yeah, I always remember one of the things that we always said when we talked to the marketing people was that it has to be instantly recognisable as a JCB Fastrac. So that set the sort of bounds about how much you could change it, really. Another one here from Simon. He's interested to break down the CDA. We said it was 2.4, so what's the actual CD?
Oh,
so
wow.
If I remember, we had a frontal... Yeah, correct me if I'm wrong, actually. I think we had a frontal area of just under 5 square metres, which would mean that the CD was about 0.5.
Yeah,
I think that's about
right.
where we got to.
Yeah, it was, and we actually went out and performed some coast down testing with a standard Fastrac machine to give us what the benchmark was for that. So that's where we just accelerated up to speed and then put the machine in neutral and measured the distance and the time that it took to coast down, and then we sort of calculated both the rolling resistance and the CDA from that.
So 0.5 obviously sounds quite high for people used to streamliners, and if I remember, the Diesel Max car we did was 0.14.
Yes.
Okay, I'm just looking at the questions, see if we've got a few more in. One here for you, Alex, as the project manager. If you were to do it all again, what would you do differently?
Ooh, well, what would we do different? Well, I think if I was offered the opportunity to do it again, I'd obviously like to go a bit faster, so we could maybe squeeze a bit more power out of the engine. I'd also quite like to do it autonomously as well. So, you know, it would take out a bit of the risk of having a driver sat in there. The machine, so the tractors today can pretty much drive on their own in the field. They're all GPS steered, and because we use the same steering system as a standard tractor, we could quite easily tap into that and get it to steer itself. And a lot of the other machine functions are all automated. I mean, when the driver gets to the end of the field, he can just press a button and it'll automatically change the engine revs, change the gear ratio, lift the implement up, steer at the end. And, you know, so they can pretty much drive themselves already. So I think that would be quite interesting to make it go quicker and for it to drive itself.
So that's the engineer's answer. And I'm sure the marketing people would say, well, what about our TV program with Guy Martin? Yeah. I've got one last one perhaps here from Matthew, which I think you're best qualified to comment on. Alex, it says, would you recommend agricultural engineering? I'm a first year IMechE engineering student.
Oh, wow. Okay, yeah. Well, I definitely would. I really, really enjoyed the course at Harper Adams. I grew up on a farm, so I've always been interested in agriculture. But I think aside from that, it is a really important industry and a really interesting industry. And I think traditionally it's probably got a bit of a bad rep for being, you know, you always hear the saying, oh, well, that looks a bit agricultural. But actually, there's a lot of tech now in the agricultural industry, and especially, you know, tractors. They're really quite an automotive product now. I think we're running about 13 ECUs in our tractors today, and there's lots of suspension characteristics we've got to tune, and it is a really, really technical, really, really interesting industry to be in, and obviously people have got to eat, so it's a pretty important one too.
Yeah, I think I would just add that you know, for the car industry people who are listening, there's lots of exciting engineering going on in the off-highway and heavy-duty sectors. Quite advanced programs on autonomy, you know, alternative powertrains, using hydrogen, etc., and the whole area really of digitalization of activities, both agricultural and construction. So there's an enormous amount of engineering going on, and very modern cutting edge engineering as well. That's all the questions. I don't know whether you've got any questions, Steve.
No, I was just going to chip in and do some closing remarks and send everybody on their way.
Okay.
Sounds good.
Excellent. Well, firstly, a big thank you to Alex, especially for a fascinating glimpse, and Alan also with the supporting comments and excellent moderation. I think we've learned a lot about what it takes to make the world's fastest tractor. I think we delved into weight reduction, aerodynamics, and powertrain performance and everything. So managed to cover off pretty much everything there, and a good round of questions as well. So thank you very much, everybody, for your time. We're just leaving you with a screen in front of you that talks about how to become a professionally engineered, but I also want to give a couple of plugs for upcoming events. Don't forget, tomorrow and Thursday is the International EV Battery Conference. So you can get to that on the IMechE events page, and then also the next Powertrain Systems and Fuels Group event is the High Performance Powertrains seminar on the 25th of November. So check those out on the events page of the IMechE, and in the meantime, have a good rest of your day. Thanks then. Goodbye.